Hello students, in the previous lecture we had seen what is relativity, then what are the frames of reference and what are the different frames of reference, and we had mentioned that we will be studying in this section only the inertial frame of reference. That means when there are two frames, then one is moving with respect to other frame with the same speed, or both are at rest. So they are in the state of the inertia. So they are called as the inertial frame of references. Now we'll study here the concept of the relativity given by Newton, and it is called as the Newtonian relativity. Now suppose we have two frames. Now example, one frame is the road on the earth, other frame is the floor of the bus. So these are the two frames. Now suppose in the bus, let us say it is moving uniformly, and the observers make some observation or make some measurement. They may find some value of the physical quantity like distance, velocity, acceleration, force, and so on. Now, what will be its value as observed or measured by the observer on the road, that is in the other frame? Now the relation between the two is given by what are called as a transformation equation. Suppose we have value as noted in the second frame, how to get the value as observed or measured in the first frame, or vice versa. Now these equations are called as the equation of the transformation, and Newton used what are called as a Galilian transformation. We have here two frames of references. The first frame, that means first coordinate system, with the origin O, and the second frame or second coordinate system with the origin O dash. In this case, the second frame is moving with respect to the first frame toward the right with the uniform speed v along the x-axis. That means if person is in the first frame, then you'll observe that second frame is moving the velocity v away from him. Also, suppose observer is in the second frame, he will observe that first frame is moving toward the left with the velocity minus v in opposite direction. So these are the two inertial frame of the references. Now here we take a simple case that second frame is moving along the x-axis with respect to the first frame. Now let us say that at the start O dash coincides with O. That means at time t equal to 0, O and O dash coincides. So that is at the start. As the time passes, O dash will move away from O in this direction toward the right, velocity v. Now after time t, O dash reaches from O to this position. So distance traveled here is O dash, and time taken to move from this point to this point is t. We use the formula velocity equal to distance by time. So distance here is O dash, time is t, so O dash is equal to v into t. Now these are two frames of references, one with the origin O, other with the origin O dash, as we have mentioned earlier. Now let us consider the point P. Now this point P, we can specify its position by using the frame. So the point P, its coordinate with respect to the first frame, that is in the first frame, that means with respect to origin, is x, y, z. We have also mentioned there one more coordinate, a time, because we can find the position at different time. So it is a four-dimensional now. X, y, z, their distance, and the time is another coordinate. So x, y, z, their distance, we call it as a space, and t is a time. So space and time. So we represent here space as well as the time. So x, y, z, t are the coordinates of the point P. Now here x coordinate with respect to the first frame, that is with respect to origin O. If you drop here perpendicular from the point P, it will fall here at M, and distance of that uh, M from the O is x. So that is x coordinate. Then in the second frame, see in the second frame, you drop perpendicular here, it will fall at M, and distance from O dash, that is a coordinate with respect to the O dash, and that is a x dash. So that's what we have mentioned. So the point P has the coordinates in the first frame x, y, z, t, and in the second frame, means with respect to the origin O dash, it is x dash, y, z, z dash, and t dash. X dash, y, z, z dash, and t dash. Then next you consider this OM equal to O dash plus O dash M. See, OM equal to O dash plus O dash M. Now OM is the distance from the origin O to that point where the perpendicular has fallen from the point P, and which is nothing but the x coordinate in the first frame, that is x. So OM equal to x. O dash equal to VT, we already mentioned this in the previous slide. Then O dash M is distance from the origin of the second frame to the point where perpendicular from the point P has fallen. So O dash M is a coordinate, x coordinate of the point P in the second frame. So O dash M equal to x dash. So we get x equal to Vt minus x dash, therefore when you simplify this, you get x dash equal to x minus Vt. Now since the second frame is moving with respect to first frame along the x-axis, so y coordinate will remain same. So y dash equal to y, z coordinate remains same, z dash equal to z, and this, let us say that these positions are found at the same time in both the frames at the same instant. So t dash equal to t. So we get here four equations: x dash equal to x minus vt, y dash equal to y minus y dash equal to y, z dash equal to z, t dash equal to t. Now these are the equations, four equations. They are called the equations of Galilian transformation. So next, I introduce to you another term used in physics, what is called invariant. Now meaning of the variant is something which is varying, and the meaning of invariant is something which is not varying, something which is not changing, something which remains constant. We don't use the word variant, we use the word invariant for something which is not changing, and we'll use the word non-invariant to tell that something which is changing. Non-invariant, not changing, that means it is a changing. So when we say invariant, that means it is not changing, and when we say non-invariant, it means that it is changing. Okay, now physical quantities. Physical quantities means distance, velocity, acceleration, time, momentum, force, etc. So these are physical quantities. The physical quantities are said to be invariant if they remain same under the given transformation. That means Given transformation means we have two different frames. If you measure the physical quantity in one frame and also measure the physical quantity in the other frame, the values will be same. Then those physical quantities are said to be invariant. So whether you measure it from the first frame or from the second frame, the event which is taking place, the value of that will not change. It remains same. That means they are invariant. So this is the meaning of the word invariant. Now let us see the concept of invariance in this Galilian transformation in mechanics. Mechanics means study of the motion. Now let us consider the invariance of the space. Space means a distance. Now suppose there are 2 points. Suppose there are 2 points. Now uh, you find a coordinate at the same instant. Suppose in the both the frame you are finding the space. That means that position at the same instant. So the time t1 equal to t2 equal to t. So t1 and t2. So the 2 points you are finding the coordinates at the same time. So t1 equal to t2 equal to t. Then in the first frame with the origin O, then the coordinates of the 2 points will be x1, y1, z1, and the position of the second point will be x2, y2, z2. Now distance between these 2 points is given by distance formula, and distance formula, the distance between the 2 points as measured with respect to the coordinates in the first frame is given by the formula root of x2 minus x1 square plus y2 minus y1 square plus z2 minus z1 square. Then this distance between the 2 points, with respect to the second frame, that means with respect to origin O dash. So coordinates of the first point is x1 dash plus y1 dash plus z1 dash, and the coordinate of the second point is x2 dash, y2 dash, z2 dash. The distance between these 2 points with respect to the second frame is s dash, and by distance formula it is square root of x2 dash minus x1 dash plus y2 dash minus y1 dash square plus z2 dash minus z1 dash square. Now we have to find out whether these two values are equal. If the two values are equal, that means the distance is invariant. If the two values are different, that means it is non-invariant. So let us find out whether it is a variant distance in the Galilian transformation is variant or that is invariant or non-invariant. Now to find out the relation between the two, we see this according to Galilian transformation, x dash equal to x minus bt, y dash equal to y, z dash equal to z, t dash equal to t. So here what happens is y2 dash equal to y2, y1 dash equal to y1, z2 dash equal to z2, z2 dash equal to z1. Okay, so these two terms will be same. Now let's consider the first term. Say x2 dash minus x1 dash. According to this Galilian transformation, x2 dash is x2 minus vt and x1 dash is x1 minus vt. Now here what will happen is this minus vt and minus plus vt cancels. What remains is x2 minus x1. So x2 dash minus x1 dash equal to x2 minus x1. So that means all these three terms in the first equation as the second equations are same. That means s equal to s dash. That means whether you find a distance, see their positions may be different in the two different frames, but if you find the distance between the 2 points, the position of a given point will be different in the two frames, but distance between the 2 points in the two frames will be same, s equal to s dash. So we say that distance between the 2 points is invariant. Invariant means remains same, not changing under the Galilian transformation. Now next we'll see if the time interval between the two events is changing or remains same in the two different frames. Now in the first frame, we call it as a frame S. Time interval is delta t equal to t2 minus t1. So first event has taken place at the time t1 in the first frame, and second event is taken place at the time t2. Then in frame S dash, time interval is delta t dash, and this is equal to t2 dash minus t1 dash. So first event has taken place at the time t1 dash in the first frame and time t2 dash in the second frame. But we have seen that in the Galilian transformation, t1 equal to t1 dash, t2 equal to t2 dash. So both these are equal. That means this difference is equal. So delta t equal delta t dash. So this delta t is a time interval between two events in the first frame, and delta t dash is a time interval between two events in the second frame. And we find here they are same. That means they are not changing. That means the time interval between two events in the is invariant under the Galilian transformation. So that means so far what we have seen is the distance remains same. Distance between the suppose the body is moving and it is at the two different points, then distance between them, whether we measure in the first frame or the second frame, it is same. So the distance is invariant. Then time interval also, time taken to go from the first point to the second point in the first frame or from the second frame, the value is same. So time is invariant. Now similarly, a mass. See, according to the Newton's mechanics, see, mechanics means study of motion. Now, Newton said that the mass is a quantity of the matter in the body. So, whether the body moves or at rest, moves with whatever speed, the quantity of the matter in the body does not change. So, it should not depend upon the velocity. That means, so whether the body of certain mass is in the second frame, you find its mass, or you find from the first frame the value of the mass remains same. That means mass is also invariant. The value of the mass, whether you measure in the second frame or on the first frame, according to Newton, it remains same. So mass is invariant. Next, we'll find out if the velocity with which the body moves and velocity measured in the first frame and the second frame, whether the values are equal or not. That means whether they are invariant or non-invariant. So to find that, we have a Galilean transformation of the distance, position. So x dash equal to x minus vt, y dash equal to y, z dash equal to z, t dash equal to t. To get the velocity, you differentiate with respect to time. This t dash equal to t. So differentiate with respect to t or t dash. It will not make any difference. When you differentiate this, it is dx dash by dt. And when you differentiate this, it is dx by dt minus velocity is constant. So v is here. And dt by dt is 1. So what you get is dx dash by dt equal to dx by dt minus v. Dx dash by dt is nothing but the velocity, the rate of change of displacement is the velocity in the second frame. That is ux dash, u is the velocity, ux dash. And dx by dt is the velocity, that means rate of change of the displacement in the first frame. So that is ux. And here v is there. So u dash x equal to ux minus v. Then see y dash equal to y, when you differentiate, you will get same thing. Dy dash by dt equal to dy by dt. That is ui dash equal to ui. Then dz dash by dt equal to dz by dt. That is this uz dash equal to uz. Then t dash equal to, if you differentiate, you will not get anything there. So we get here, see, this is what we have shown the motion in the one dimension. So velocity, if you measure in the first frame or second frame, is not same when it is moving along x-axis. Suppose it moves in the plane, in the space. So everything will change here. So u dash y will be also not same as uy, uz dash is also not same as uz. So in general, see the displacement x minus vt is not equal. Okay, in three dimension, in the when the body is moving in the space, even y dash will not be equal to y, and z dash will not be equal to z. So this displacement is non-invariant. It is changing. It doesn't remain same. It is changing. So non-invariant. Then velocity is non-invariant. So this is a Galilean transformation of the velocity. Next we'll see that suppose body is not moving uniformly but it is accelerating, and we find the acceleration whether it remains same in both the frame or not. That is what we want to find out. Now to get acceleration, we have formula for velocities. You differentiate it. If you differentiate the velocity with respect to time, you get the acceleration. So if you differentiate with respect to time here, ux dash by dt equal to ux by dt minus v is constant. So derivative of v with respect to t is 0. So what you get is dx dash by dt equal to dux by dt. That means expressions are equal. Ax dash equal to ax. Similarly, ay dash equal to ay and az dash equal to az. So here we find that accelerations are equal whether we measure in the first frame or from the second frame. So that means acceleration is invariant. That means it remains same, not changing under the Galilean transformation. The next, a Galilean transformation of the force. So let us say, suppose the force is applied. When a body is excited, means force is applied. If you measure the force in the second frame and then you measure the force in the first frame, whether it is equal or not. See, this when you measure the force in the second frame, it is F dash, and as we have seen earlier that according to Newton, mass remains constant. So m, acceleration in the second frame is a dash. But we have seen that here that a dash equal to a. The acceleration remains same. So a dash in the second frame is a. So m into a. So now this a is in the first frame. So that force we call it as F. So we find that the value of the force, whether you measure in the second frame or first frame, is same. That means the force is also invariant, not changing under the Galilean transformation. Now, so far we have seen that the physical quantities are invariant or non-invariant. Next, with the laws in physics, whether they are invariant or non-invariant. So, laws in physics are said to be invariant if their form remains same under the transformation. That means, say, the physical quantities are invariant if their values remain same in the two different frames. Laws in physics are said to be invariant because every law has some equation, mathematical equation. The form should remain same. Then it is called as a invariant. See, invariance of the principle of the conservation of the linear momentum. See, the conservation of linear momentum, that m1 v1 plus m1 u1 plus m1 m2 u2 equal to m1 v1 plus m2 v2. And one can show that the form of that equation remains same. See, m1 u1 plus m2 u2 equal to m1 v1 plus m2 v2. So here what happens is in the second frame it will be m1 u1 dash plus m2 u2 dash equal to m1 v1 dash plus m2 v2 dash. So these equations on both the sides of both the equations will be same. We need not prove that, but if it is very easy, we can show that it is invariant under Galilean transformation. Then invariance of Newton's laws of motion. See, Newton's laws of motion, the first law of motion, that is the qualitative statement. Qualitative statement that body at rest remains at rest, body in motion continues to be in motion unless acted upon by external force. Now, the quantity of that force. So the second law gives the quantity of the force. Force equal to mass into acceleration. So it gives a quantity. It quantifies. Okay, and we have shown that F dash equal to ma dash, and that is equal to ma. A dash equal to a because acceleration is invariant, and ma is nothing but the force in the first one, that is F. And we find here that F dash equal to ma dash, F equal to ma. So form, that force equal to mass into acceleration, the form remains same. So we say that Newton's second law is invariant under the Galilean transformation. Form the equation remains same. Now, here we have seen so far that the fundamental quantities like a distance, time, and mass are absolute quantities in Newtonian relativity. That means that value, absolute means that value does not depend upon the frame. In whatever frame you may measure, we have seen that distance remains same, time remains same, mass remains same. Okay, so they are called as the absolute quantities, and that is according to Newton relativity. In the previous slide, we had seen that main physical quantities in the mechanics, in the study of the motion, remains same whether you measure from one frame or the other frame. The values of the distance between the 2 points, the values of the mass, value of the time, it remains same. So they are invariant uh, under the Galilian transformation. So according to Newton's relativity, the values of this distance, time, and mass remain same. Now, one is the mechanics, Newtonian mechanics. Okay. Other is what is called as the electrodynamics. Electrodynamics, electromagnetic theory. Now, this electromagnetic theory, it is based on one equation. Okay, we are not studying this equation. We have electrostatics and magnetostatics. Electrostatics you are studying in semester 5. Magnetostatics you will be studying in this semester. But electromagnetic wave will not be studying, not part of the syllabus. It will be studied at postgraduate level. But this is the equation of electromagnetic wave equation. We have something called as electromagnetic wave, that dou 2 phi by dou x2 plus dou 2 phi by dou y2 plus dou 2 phi by dou z2 minus 1 by c square dou 2 phi by dou t2. This phi is nothing but the potential. Okay, and this is equal to 0. Now, if you find the form of this equation, in the first frame and the second frame, then the form changes. Form does not remain same. Like in mechanics, like a force, the form remains same. Force equal to mass into acceleration. But form of this equation, now this is a form of the equation in the first frame. If you try to write down in the second frame, it will not be same. That means it is non-invariant. That means it is changing under the Galilian transformation. The proof of that is not in the syllabus, but those who are interested, you can refer the book by Garage. It is there on the page 15. So now in general we can say that electromagnetic wave equation is not invariant under the not invariant means non-invariant under the Galilian transformation. So now here what happened? That means what happened is Galilean transformation cannot completely describe the situation in physics. In mechanics, it gives a invariant result, whereas in the electromagnetic theory, it gives a non-invariant result. Now, in the relativity, we require two frames, one at rest, other moving. The Newton was looking out for the frame of reference which is at rest. See, Earth cannot be considered to be the frame at rest because Earth is rotating and it is also revolving. So it is accelerated. So it's not inertial frame of reference. So Newton was looking out for some inertial frame of reference. So he said that the stars should be considered as the inertial frame of reference because uh, according to Newton, the stars are at rest because the position of the star normally relative position does not change. So Newton thought that they are at the rest. But later on, once what is called a Doppler's effect of the light was given, then they came to know that even the stars are not at rest, but they are moving. So then the other scientists were looking out for some inertial frame. Then one scientist said that we should take what is called the ether as a inertial frame of reference. Now this concept of the ether was given by Huygens while giving this wave theory of light. according to wave theory of light, the light is propagated by means of a wave. And then there is a controversy that if it is a wave, then it requires a medium. Mechanical wave requires a medium, and light travels from sun to the earth. In between, a vacuum is there. So how light can travel in a vacuum? So in order to support his theory, Huygens said that there is a medium called as the ether, and that ether is there everywhere in the space. Even in the vacuum, that ether is there. And its property, it has no property other than to transmit the light. It has no mass, it has no property, except its job is to transmit the light. So this concept of ether was given, and that was given by the Huygens. And some scientists, they said that ether should be taken as the um, reference point, because ether is at a rest. So ether should be taken as a reference point because it is at rest. So it can be considered to be at rest inertial frame of reference. So that was considered. But later on it was proved that ether does not exist. In fact, in the next chapter we will prove that something called ether does not exist. Okay. Then the theory, all theories start there to change. Then somewhere around 1900, the scientist known as Maxwell, he gave another theory of the light. See, Huygens had said that light is a wave, but the problem was that how the light mechanical wave can travel through the vacuum. So Maxwell, he developed a theory. He said that light is a wave, but not a mechanical wave. It's not because of oscillation of the particle, but it is because of oscillation of electric field and magnetic field. It is an electromagnetic wave. See, Maxwell said that light is a wave, but it is not a mechanical wave. It doesn't require a material medium to get transmitted. It's not because of the vibration or the particles, but it is because of oscillations or oscillation of the electric field and the magnetic field. And he called that wave as an electromagnetic wave. And electromagnetic wave, electric field and the magnetic field can exist even in the empty space, that is a vacuum. Even in a vacuum it can exist. So the Maxwell theoretically proved it that light is an electromagnetic wave. So it can travel even in the vacuum. So the concept of ether was not required. Then he also proved theoretically that the light travels in a vacuum with same speed c. C is 3 into 10 raised to 8 meter per second. In all directions, in all frames, in same speed. So what happens is the velocity of light will not depend upon the frame of reference. Suppose a light is traveling, so photon is moving. Whether you measure it from one frame or other frame, value remain same. It is not like see, suppose you are traveling in the car and another car is traveling in the front of you. Then you will find that if the car which is moving in front of you is moving at a certain velocity, then the car in which you are moving, you will observe that it is not moving, it is moving with the difference of the velocity of the second car and velocity in which car you are moving. Okay, so it is depends upon the frame, two cars, two frames. But the light is not like that. Suppose photon is moving, and whether you measure from one frame or other frame, the value will be same. So we say that velocity of the light is absolute. It has the same value in all the frame. Now this was proved theoretically by Maxwell, and later on some scientists also proved experimentally that the velocity of light is absolute. In a given medium, it moves in a same speed whether you measure from one reference frame or another reference frame. But according to this Galilian transformation, in the frame S, suppose light is moving, so Ux equal to C. In the frame S dash, u dash x equal to ux minus v, that means the velocity will be c minus v. And so in the xy plane, now this is moving along the x-axis. Suppose it is moving the xy plane. The value will vary from c minus v to c plus v related to the frame s. So here what happened is, in the two different frames, you see that velocity light is different. So Galilean transformation, that means Newton's relativity, it says that the velocity of the light is different if you measure from the different frame of reference. So under Galilean transformation, that means in the Newton's relativity, velocity of light is non-invariant. So it is varying under the Galilean transformation. That means it is not absolute. But that is what Newton was saying. But later on, according to Maxwell's theory, and also experimentally is verified, that velocity of the light is invariant. The value remains same whether we measure in one frame or other frame. That means velocity of the light is um, absolute. So this is this was the defect of the Newtonian relativity. Now, according to Newtonian relativity, we have seen that the laws of mechanics, that means example second law, force equal to mass and acceleration, is invariant under Galilian transformation, whereas law of electrodynamics, that electromagnetic wave, in the two different frames the form is different, so it is non-invariant. So the scientists thought that this is happening because of the wrong transformation, okay, and because for a different frame, different laws are to be devised, okay, and so they are looking out now for some frame which will give. So they are looking out for some frame called the absolute frame of reference, where the laws in the mechanics and the laws of the electrodynamics, that means electromagnetic theory, in both the cases they have to be invariant. So they are looking out for the same. They call it as the absolute frame of reference, and they took that absolute frame of reference as the ether. That's what I had mentioned earlier. Okay, so Newton's theory of relativity was considering the ether as the absolute frame of reference.